Today we will review the rules of exponents and radicals. First we will focus on exponents. Exponents are expressed in the form of a to the nth power, where a is any real number and n is a positive integer. So if we look at a to the sixth power, it's the same thing as multiplying a by itself 6 separate times. Or in our example below, 3 to the fourth, we see we have 3 multiplied by itself 4 times. Our chart on the right quickly summarizes all the rules that we will review. The first rule we have is the product rule. When you multiply exponential expressions with the same base, we keep the same base and add the exponents. So in our example, where we have 2 to the third power times 2 to the fourth power, we see that our base remains the same, but we add our exponents. So once we add our exponents, we would have 2 to the seventh power. The same can be done with variables, where we have x to the ninth power multiplied by x to the fourth power is the same thing as having x to the 13th power. We use the product rule when you raise a power to another power. We keep the base and multiply the exponents. So an example where we have 5 to the third power squared is the same thing as having 5 to the 3 times 2 exponents, which will give us 5 to the sixth power. The power rule for a product is when we raise a product to a power, we raise each factor to that power. So if we have 6 times a times b squared is equivalent to having 6 squared times a squared times b squared, or 36 times a squared times b squared. Then when we have the power rule for a quotient, we raise the quotient to a power. We raise both the numerator and denominator to that power. So we see we have here x over 5 to the third power is the same thing as having x cubed divided by 5 cubed, or x cubed over 125. A simple rule to remember is 0 as an exponent. When we have any exponent to the 0 power, our product will always be 1, no matter what the base is. When we have a negative exponent, for example, if we have 3 over 4 to the negative fourth power, we can take the reciprocal of our fraction, which would result in 4 over 3 to the fourth power. Then by applying the power rule for a product, we can get 4 to the fourth power over 3 to the fourth power. If we have two negative exponents written as a fraction, we can rewrite the original expression with only positive exponents by switching their positions in the fraction. So we see below we have 2xy to the negative cubed over 3z to the negative second power. If we switch our fractions, where our 3 is on top instead of the bottom, and our 2 is on the bottom instead of the top, our exponents go from a negative exponent to a positive exponent. If we have a fraction that both involve exponents and have the same base, we can subtract the denominator's exponent from the numerator's exponent. So we see we have 3 cubed over 3 to the fifth power. If we take the numerator's exponent subtracted from the denominators, we'll get 3 to the negative second power, where we can make that a positive exponent by having 1 over 3 squared, or 1 over 9. There's a quick summary of our rules for exponents, and once again, our rules are summarized in the chart to the right. When we deal with radicals, we'll usually be dealing with square roots and cube roots. First, let's learn how to simplify a square root. So if we take our example down below where we have the square root of 75, we can break 75 into two values. When multiplied together, we'll get the product of 75. So we can see that 25 times 3 equals 75. And then if we individually take the square root of our two values, we can see that the square root of 25 is 5, which will bring that 5 outside the square root. But since the square root of 3 can't be simplified anymore, the 3 will stay within our square root. When evaluating radicals, if n is a positive and even integer, then the square root will cancel out and will give us an absolute value of a, which we can see below. However, if n is a negative or an odd integer, then the square roots will cancel out and we will just get the value of a. We can see in the example below, the cubed root of 3 to the third power is the same thing as 3. If we have an expression where we have the base to 1 over the nth power, if n is a positive integer and greater than 1, we can rewrite it as the n to the square root times a to the nth power, which we can see in our example where we have 5 to the 1 over 3 power can be written as the cube root of 5 to the third exponent. If we have a value that is expressed in the form of a to the m over nth power, and m and n are in the most simplified form, the denominator of the fractional exponent is the index of the radical, and the numerator is the power to which we raise the radical expression. So we can see below we have negative 64 to the 2 over 3 power, which we'll see that our denominator can be placed in the index of the radical taken by the square root of 64, and where our numerator is the power to which we raise our radical expression. So our radical expression is squared. When we multiply square roots and our bases are non-negative and real numbers, we can multiply both bases underneath the square root, as seen in our example below, where we have the square root of 2 times the square root of 6 is the same thing as taking the square root of 2 times 6, which can be written as the square root of 12. The quotient rule for square roots is if a and b are non-negative and real numbers, then the square root of a fraction, we can break our square roots. We can have our square root of our numerator over our square root of our denominator, which can then be dealt with individually, as we see that the square root of 9 is 3 and the square root of 36 is 6. When adding and subtracting radicals, we can only do so when the radicals are alike. So in our example, we see the square root of 4 is the same for both radicals. So we can add the values outside the radicals together. And we can see we'll get 8 times the square root of 4. And when we are multiplying radicals, we can multiply radicals when our radicals are the same underneath our square root. We can multiply the values outside our square root. So we can take 3 times 4 to get 12 times the square root of 4. And it's important to know that when dividing radicals, radical expressions are not in their simplest form if the denominator contains a radical. We can eliminate the radicals from the denominator by multiplying the denominator and the numerator. So in our example below, we have 36 over the square root of 18, where we can simplify this down to 12 over the square root of 2 to get the square root of 2 out of the denominator. We can multiply the numerator and denominator by the same value, which will cancel the square roots in the denominator, leaving 12 times the square root of 2 over 2, which can further be simplified into 6 times the square root of 2.